Yeah. So hello everyone. Welcome to CeADAR Tech Talk series. For the seminar today, we have Dr. Saeid Homayouni, who is an associate professor on environmental remote sensing at the National Scientific Research Institute, Quebec, Canada. And today, Saeid will talk about the application of RADARSAT Constellation missions in for crop monitoring and mapping. I hand it over to you, Saeed.
Okay, thank you for invitation. It's my pleasure to present some of our works here in Canada, and it was mainly on using the radar remote sensing and earth observation for agriculture application. Here I present two applications on crop mapping and crop monitoring. So maybe before I start, I can introduce myself. I did my PhD in signal and image processing in Paris, Telecom Paris, and then I was working on a European project called PIM-HI, the multi and hyperspectral platform for environmental monitoring and mapping in Bordeaux. And then I moved to Canada, and I worked for Agriculture Canada, and recently I joined the Institut National of Scientific Research, and I'm working at the Center for Water, Earth, and Environment. And since last year, I started to initiate my research group, and I called it Group on Earth Observation Analytics by Artificial Intelligence, or GeoAI. So this is a very common name, but everybody talk about GeoAI for geospatial and remote sensing data. And I'm presenting this result on behalf of my colleagues, Dr. Heather McNairin, who is very well-known and talented research scientist at the Government of Canada, Ottawa Research and Development Center. My former postdoc, Mehdi Hosseini, who is now is in Maryland on the JCAM and GeoLab Agricultural Research Center. Dr. Andrew Davidson, who is the Director of Earth Observation Group at Agriculture Canada, and my former PhD student, Masoud Mahdian, who is now a professor at Memorial University. So here you are, the outline of this presentation. So I will talk a little bit about the importance of research and earth observation in agriculture and precision agriculture. I present the project that we were working on, and very short introduction on SAR and polarimetric remote sensing, and the two applications that I prepared. So as I wanted to keep this introduction and presentation very simple and general, so I didn't go to the technical detail of the SAR, polarimetric, and the algorithm. So as you know, SAR is relatively more complex than optical remote sensing, but I try to stay simple. But if you are interested and if you have any question, you are welcome to ask me, and maybe I can later provide the answer or more information for you. So normally all the papers and presentation about the application of remote sensing in agriculture start to talk about the food security and resources. So you know that maybe right now we have around 8 billion people in the world, and the food security and the resources are a main issue for our generation. And considering that the increase in population in the future is really a challenge that we, as the scientists, we need to work on and find a solution. So as you know, our resources are very limited. For example, in the left, you can see the map of the fresh water, and we know that the amount of water that we can use for for agriculture and for our needs is very limited. And at the right, you can see the fertile soil that we can actually use for the agriculture, cropping and activities. So from here we can see that our resources are very limited and the needs are very big. So we need to find really a good solution. And from here I can jump into the topic, and based on this low chance, we need high potential observation, and this is why we are shifting from optical Earth observation to radar observation that can provide better data in terms of quality and the coverage, especially in the northern hemisphere that is almost cloudy. So the solution is not new, is provided by various scientists and is called normally sustainable agriculture. So as you know, in the sustainable agriculture, we are involving people, economy, and planet itself. So we are providing the food for ourselves, for our generation, by improving the economy of farmers and the society, and protecting the planet, because this is not only for us, for our next generation, for our children and grandchildren as well. So we need to protect it. So the solution and the tools here can be precision agriculture that can provide can help us to reach the goals and objectives of sustainable agriculture. So as you know, precision agriculture is a farm management system based on the right source, with the right rate, at the right time, and in the right place. So you can see 4 R in that, and this 4 can be logically connected to the accuracy and to the good quantity of the things, and at least the last one, right place, is something that fall in the field of geomatics and remote sensing, that we need to know exactly our parcel and our field. So for example, the goal of precision agriculture is to provide a kind of decision support system for the whole farm management, with the aim of optimizing the return on input while preserving the environment and resources. So we are using satellite, weather data, Internet of Things, mobile technology, and robotics. So all is together working on providing the high return, the word is I use normally the French in my presentation, the rendement or the return. So it's all to provide the better income for the farmers and protecting the environment. So the concept of digital farm or a smart farm is actually very, very popular these days. So everything is connected via internet, and we are using UAV, geosensor, robotics and machinery, Internet of Things, and also big data and artificial intelligence to provide reliable, accurate, and up-to-date information for both farmers and farm managers, and also sometimes for the scientists who are working in this field. Just for your information, we are running a special issue on open access journal, Agronomy and Remote Sensing, and the topic is smart agriculture. So all the application of the deep learning and AI for any type of data, from geosensors to remote sensing sensor and drones. So you are welcome to visit the page and publish, submit your paper if you would like. So as I mentioned, our role as a geoscientist and geomaticians is to provide the best data, and we can provide this data by surveying, by GPS, global navigation systems, airborne photogrammetry, satellite remote sensing, UAV imagery, LiDAR, and of course geospatial analysis and GIS. So we use all these technologies for data collection, for data processing, and for data presentation. So all falls in our field of expertise. So what we do normally, for the precision agriculture, we need management zones. And by management zones, I mean a homogeneous zone within your field, within your agriculture field and parcel that has similar characteristics. So this is important because, for example, if this part of your field is suffering from any kind of parasite or problem like hydric stress or drought, you can apply a kind of prescription or find a solution for that. But before that, you need to know that part of your parcel, and you can map those areas using geospatial technology. So it's a very schematic, simple model that normally I present to my student, that we need to model the real world because it is big, because we can't work with all aspects of the planet. So we model it in your computer using analytical approach. So we need two types of data: geometric information like the coordinates, and non-geometric information like soil type, soil texture, soil moisture, temperature, and any other parameters. So we put all together as the different layers and apply the geospatial analysis to map the management zone, and then apply the fertilizer at the good rate, at the good time, and at the good place. So, and these days, you know that for almost different application, we are using for new technology that I called them the four revolutions. And you know that open data, cloud computing, open source programming technology, and artificial intelligence and deep learning are changing the landscape of Earth observation in general, and especially for the agricultural application, because as I mentioned, it's really important. And every year from the beginning of season, you have to repeat the last year activities within the same context and within the same challenges. So it's ongoing procedure, and it's endless as far as we know that we need to provide the foods and protect the environment. So as I mentioned, the whole activity that we are involved in this context is using remote sensing to provide the high accuracy, up-to-date and reliable data. And you know that we have two technologies of remote sensing Earth observation: the passive and the active sensor. So in passive, you know that we are relied on the natural light resource or sunlight, and we use optical, including multi and hyperspectral imaging systems and technology, and also thermal and microwave remote sensing that are based on the natural source of energy. But in parallel, we can use the active technology. That means we have the source of energy on the platform, on the satellite, and we can generate the electromagnetic signals and to the sun or planet, and receive the reflected or here backscattered energy, and do object detection, classification, or any application. So mainly we are working with the radar or SAR systems, and also we have LiDAR in this category. So it's really important for high accuracy and large scale mapping, like the canopy or even the soil topography, microtopography in some cases. So the radar or SAR signals are very interesting, and as you can see here, and I mentioned, I think that compared to the optical remote sensing, SAR systems are more complex, and lots of parameters play an important role in the characteristics of the data, like frequency. So as you can see here, if in optical data we have a spectral bands, here we have the frequency, or we can convert it into wavelength, but because the radar is developed essentially by the electrical engineers, they use lots frequency instead of wavelength. So we have low frequency and high frequency, and as a rule of thumb, you know that if the wavelength is higher or frequency is lower, the penetration power is higher. So you can go to the canopy and you can observe the structure of branches, leaves, and canopy, and that in some cases is very important. The incident angle is very important. Normally in the optical remote sensing, we use the nadir imaging, but as you know, radar systems are side-looking systems, and there is mathematical and physical reasoning behind that. But we are normally looking at the left or at the right of the orbit or the airplane trajectory. So that impact the observation if you are looking very low incident angle or high incident angle. The polarization is something natural with the electromagnetic energy. I come back to it, but we have different type of polarization. Geometry, for sure, the surface geometry or the object geometry in general is really important, and the radar signal is sensitive to as well. And the dielectric constant and the water contact of your media and object is really important and affect the quality of the observation. So here just okay, sorry. Here I simply provide two examples of Sentinel-1 at right and Sentinel-2, the optical sensor at right, at left. So as you can see, and as I mentioned, optical data are very good, and we did lots of good works and developed lots of efficient algorithm. But we know the limits of this type of data, especially in the northern hemisphere. We have almost cloudy skies, and if you work in a region that the chance of clear sky data is very low, so you need to switch to radar and SAR remote sensing. And you can see the radar data looks like noisy and ugly in some cases, but if you look with the good eyes, you can see the potential of this data for here for crop mapping. And as you can see, lots of parcels are presenting with different colors and information, so they are very informative and helpful for agricultural applications. So about the polarimetric, as I mentioned, is one of the most important and also challenging parameters in remote sensing and in SAR remote sensing. So in the past, we had the RAR, Earth Observation System, called Real Aperture Radar, but the resolution was quite low. And later, the engineers developed new technologies called SAR, synthetic aperture radar, based on the Doppler phenomena. And by using this concept, we can increase the resolution by sending and receiving multiple pulses from the same area, and you can produce a very high quality, high resolution SAR image. And this is based on the electromagnetic signal that we can produce, and sent to the send. So based on the polarization, and polarization is a kind of um, waving behavior of the light and the energy in the space. So we have two fields of electric and magnetic fields for the signal, and that can produce an electromagnetic signal propagating in the space. Basically, we have a generic model for describing the wave behavior by using an ellipsoidal model, but in practice we can use two modes of circular and linear polarization for Earth observation. I come back to it in the next slide. So, for example, for linear polarization, as you are familiar, we have this polarization called sometimes copole for VV and HH. And this means that you are sending the signal vertically and receiving vertically, or sending horizontally and receiving horizontally, or in the cross pole mode, you are sending vertically and receiving horizontally, and sending horizontally and receiving vertically. So you have 4 combination, and by 4 combination, each pixel brings back 4 information, and this is information that we call intensity. And if you go toward the full polarimetric sensors, you can have 1, 2, or 4 of them. If you are using 1 polarization or 2 polarization, maybe you don't have the phase information. But when you are using the full polarimetric information, you have also a complex number for each pixel, and you can calculate for each polarization, and you can calculate the intensity and phase. And those information are really helpful for any type of object or target description and identification. So here I try to mention a few advantage of this data, and from this information, if you remember the whole concept of full polarimetric, you have a good matrix of information for each pixel, and from that matrix you can extract lots of information, and you are for sure familiar with the polarimetric decomposition. So you have the first singular matrix, and you can convert it to coherence and covariance matrix. I'm not personally expert of SAR remote sensing, but I try to understand it and use it for this application. So I know that the ESA has provided lots of lectures and training and good materials, and the software, Pulsar Pro and SNAP and open source is really interesting to use them and learn them. And from that point, I jumped to the new generation of the SAR remote sensing technology, which is RADARSAT Constellation mission. It's actually the 3rd generation of Canadian radar system. The first one was single, the second one RADARSAT 2, which is in the orbit right now, is quad pole, but this constellation consists of 3 satellites, unique satellites, identical satellite, and they provide the compact mode data. I will talk about the compact shortly. And this is a very interesting system with lots of imaging mode, and they are able to cover, for example, the whole Canadian landmass in less than 2-3 days, and with a high quality data. Unfortunately, recently we understood that the Canadian government and the space agency won't collect the data over the area outside of the Canada, just maybe for emergency and natural hazard cases, but the satellites will cover only Canada. So for the linear polarizations system, we have lots of them in the space. but for the circular is something new. And why we need circular data? Because when you have the original intensity, backscattering, and phase, you can put them on a complex matrix called normally singular complex observation, and from that you can produce various type of polarimetric information, because thanks to the magic of physics and mathematics, you can play with that matrix and provide lots of different information. So from circular polarization, there is potential to extract the linear polarization as well as the other type of polarization. So here we have left hand and right hand circular polarization, similar to horizontal and vertical polarization. And as you can see, it is a unique system so far, and only Canada has developed this kind of systems. So here is the whole approach that we developed for this work. So from the data, we extract the linear polarization and also the circular polarization. And as I mentioned, using the polarimetric theory and decomposition system, we can extract lots of SAR features, and those SAR features are very high potential. There are still some kind of correlation among them, but you can use the machine learning and deep learning approaches to use all of these features for mapping and for monitoring. This is the topic of my presentation. Oh, sorry. So the data that we used for this project comes from SMAPVEX 2012. But if you know, the series of SMAPVEX projects are the calibration validation field campaign supported by NASA for the SMAPVEX project. And SMAPVEX is soil moisture active passive mission. The objectives of this mission are to provide high, accurate, up-to-date data about the soil for both agriculture and environmental modeling, hydrological modeling. So they had, I think, maybe up to 10 different campaigns across the world, in Australia, in the US, in Canada. So I was part of 2000 campaign 2012 and 2016, but the 2012 was very successful field campaign. We were in the field for more than 6 weeks, and we collected lots of data from the space, air, and in the field. So I will show some of this data. So the region was in Winnipeg, Manitoba province of Canada. It's a very flat area, lots of agriculture system there. We select this area, as you can see, the rectangle, green yellow rectangle, which is an agriculture area, and the forest area on top left here. So we had two different soil types, and we flew over there using different sensors that I can show you. In the field, we collected lots of data, and as you can see, for each field, we observed a large test site or plot, and we collected the crop structure, crop leaves, biomass, those things, and also soil moisture, soil temperature, texture, those things. Here you can see the experimental configuration, and in the table you can see the type of crop parameters that we collected. And then for the observation data, we follow the kind of standard protocol from pre-processing, especially speckle filtering, geometric correction, and polarimetric analysis. for sure we need to extract a few or as much as possible the polarimetric features. And also we simulated because at that time the RCM has not been launched, but we could simulate the data from the quad-pole RADARSAT 2 data. We used a simulator from Canadian Center of Remote Sensing, and we created the time series for our analysis. So as you can see here, the scene was, or the study area was quite large. So we had to collect 3 scenes per day. And after all this pre-processing, we put them, or we mosaic them, and we put them in the different layer, or we layer stack them to create a kind of a spatiotemporal data stack. So we can use now this data for our analysis, and they are very well geo-referenced and calibrated in terms of radiometric or polarization calibration. So the first example or application that I want to talk about is crop inventory and mapping. So as you know, the agriculture sector in Canada is really big. Lots of people are involved, and the size of the country is really big. So we need good tools to cover these areas and these parcels, and again every season, every year. So this is a very high important, high priority mandate of Agriculture Canada. So they since 2009 they started to produce the annual crop map, and they have been using various data from Landsat, Spot, and then Sentinel data, and also different type of classification technologies and algorithms like decision tree, random forest, and they are providing some good approaches. But for this project, for our research project, we use both pixel and object-based random forest classifier. So why object-based? Because when you are working with the single pixel, especially within the SAR data, there is a chance that single backscattering, single pixel information has been affected by the speckle. So a speckle, however, we can use filtering or multilurking to reduce the speckle, but still is contaminated by a speckle. So we can enhance our strategy of classification by going toward the object base, and there are some good techniques that can produce the object and super pixels instead of single square pixel. You can irregular objects, and we call them super pixels, and you can apply the classification on these objects. Still you have series of statistical information about each segment, each object, minimum, maximum, standard deviation, or other higher order statistics of this object, and those are very actually important when you want to improve the classification. So as you saw, I am talking about the SAR observation, Earth observation, but the same approach can be applied to the optical data. It's actually or works in the parallel, because the nature is really complex. So you can say that it is my ultimate tools and solution and works very well. So you need to have a look at the other range of the region of the spectral signatures. So you can use both optical and SAR data together and provide, because the result is more important than the information and tools and theory. So you need to provide high accuracy crop map and crop information for end users. So you have to use all the possibilities. So we can apply the same approach to the optical data. So the decision tree or the classifier that we use is based on the decision tree, but using the ensemble theory. And you know that by these two together, we can provide a large number of trees, and it's normally called random forest. And random forest is a set of classifier, and at the end, you can combine the result of all these classifiers by voting majority voting. So you can count the number of corrected labeled pixels or objects, and you can, for example, say if the vote is more than something, more than the number, and you can improve the procedure. So there are some interior mechanism like boosting and bagging to improve the quality and to speed up the procedure, but this may be based on this simple structure. So for as a classifier, you know that random forest is a supervised classifier, so you need post-training and testing data to assess the accuracy of the classifier. So here we were lucky because we had a good amount of field data, and we used them for both training and testing objective and the steps of our algorithm. And you can see we covered the main crops in that region, like forage, oats, wheat, corn, canola, soybean, and there are some still not really large in terms of number of fields, but still various crop types like sunflowers and legumes sometimes. So as I mentioned, I didn't go to the details of those algorithms, but here I can just share with you the features that we extracted from the polarimetric data, like simple backscattering or sigma node in HH, HV, and VV and HH, and also the decomposition from the famous decomposition algorithm like Claude-Potier, H entropy alpha, or Freeman-Dorden, or Yamaguchi. So those are almost similar, but sometimes they provide more information. For example, Yamaguchi has 4 components. Freeman-Dorden has only 3 components, double from the soil, volume, double from the stems and the crops with larger canopy structure, volume for the canopy volume, surface for bare soil, or sometimes the after harvest. So those information are within the data, so we can decompose them and provide more meaningful features or SAR features here. And Yamaguchi has 4 components, so there is some more information. So we use them, all this information, and as you can see here, in the internal design of random forest, you can evaluate the variable importance parameter, and that is a very good criteria. There are some critiques about these parameters, but as you can see, it is providing some helpful information about the importance of some features. So for example, if you have a large area to map, you can, like PCA, select the most important PCs, maybe the first 3 or 4, and you can apply the classifier on a larger area and provide better or similar result. And you don't need to spend lots of time on processing. Here is the same concept and statistics, but about from the compact polarimetric parameters. And you can see there are more features from compact pole data, circular polarizations, and the accuracy is quite well. I can show you here. This is the result, actually, the crop maps, and however, it looked like similar, but in some cases, especially when there is a kind of heterogeneity in the field, and there is high healthy and low healthy crops in your field because of the watering, or because of the stress, or any other things like parameters like slope that affect the some pixels. But in general, you can know that the whole parcel is planted on corn or on wheat, and you can calculate the accuracy. So we calculated the accuracies of this algorithm based on these two approaches. And as you can see, for full parametric data with pixel based, we got 84, but using object based, we could increase the accuracy up to 88. And as a rule of thumb, Agriculture Canada thinks that if you provide them a kind of crop map with 85%, it is still usable for lots of application, for crop inventory, for yield estimation, yield monitoring, and helping the managers or politicians to have a good insight about the agriculture production at the end of season. And the last line, as you can see, we got similar result from the compact poll data. I recall you that we simulated this data, but we are providing, because since the last fall, the Canadian Space Agency gave us access to the data. So far, we don't have the synchronized reference data or field data for this observation because of the COVID. We couldn't get out and visit the fields last summer, but it is something that we have planned for this summer. But from the simulated data, you can see that there is a good potential to achieve the same level of accuracy. Okay. And the second application is on crop monitoring. And by crop monitoring, I mean that observing the crop growth and development over the season. And it is very helpful for agronomic management and practices to see if there is some problem anywhere in your field. So again, from the polarimetric SAR data, we extracted the information. Here we use the Freeman-Dorden because it's very informative and interesting, and represent the physical scattering characteristics of your field, volume, double, and surface reflectance or backscattering. And from them, we calculated the total power, and we can create the specific features like quad pole ratio. It is a ratio between the volume scattering to surface scattering, so that can be used to model the amount of vegetation above the ground. So we found it useful and helpful, and we extracted this from all the data that we had for different crops. And as you can see here, we have added similar features from the optical data, NDVI and SAVI. And if you are familiar with them, both are similar, but SAVI is more helpful when there is less amount of crops and vegetation in your field, so it's soil adjusted vegetation index. But in general, you can see that there is a good match between them, maybe for some crops like corn, because at the end you have different patterns, so you have fruit on top of the plant, and can be represented differently in the radar data. But in general, there is a good correlation between these two data. And I recall you again that the objective here was to see if we can produce the same result or extract the same type of information, but from the only radar data, because we already know what we can do with the optical data. So we just compare them because the polarimetric compact and quad pole data, because as I mentioned, we had the full polarimetric quad data, but we wanted to simulate the similar type of observation from next generation of RADARSAT system. And as you can see here in this graph, there is a good correlation between them or similarity. Sometimes we can see a kind of underestimation, but in general, the trend was acceptable. And here you can see the correlation values for different crops. And when we did this kind of discrimination analysis or the potential of data, information of data, we can put them in a kind of machine learning, deep learning regression model. And we did that using random forest, support vector machine, artificial neural network. And we are using a deep learning model these days. And we try to estimate dry biomass, wet biomass, and leaf area index. And as you can see, in general, we got some good results, and that can be really helpful to see in your parcel that which area had higher potential of yield, and if there is some issue somewhere, and if you do that in early stage of your crop in season, you can react and provide some, for example, fertilizer or pesticide to remove the issues. So you can see here the one-to-one graphs, and again, after individual statistical and regression analysis, we put all together, because when you are working with a large area, you can say that I am interested only in wheat or only in corn. We apply the modeling for each crops and evaluate the models, but at the end we put all the crops together and produce a kind of universal or generic model for all the crops. And you can see that still there is some good level of confidence and reliability in the modeling. And at the end you can map the parameters that you want to monitor, spatially and temporally, the crop growth. So again, leaf area index, dry and wet biomass, because sorry, the dry biomass is actually what you can get from your field at the end of season. We call it yield. But wet biomass is something that is naturally in the field during the season. So if there is some issues like hydric stress or parasite or something that affect the health of your crop, the water content can be changed during the season. So we try to map these parameters over the space and over the time, so that can be feed in the decision support system for agronomes and for farm managers. So as you saw, the objective was really to see the potential of the compact data, and we got some good results. And for both crop mapping and crop system monitoring, pardon. And we are hoping that the Canadian government open this data and we can apply the similar approach to real data and help farmers and farm manager to high potential data for their daily activities. And as you saw maybe in the interview that I did with your colleagues, our team objectives is to put all these analytical tools and approaches in a online platform or mobile platform and provide the real time data to the farmers, and they can use this in the field on the time and react to protect to guarantee their revenue and economic situation and also protect the environment. I just put the two papers that we got published from this project. Actually, the project with Agriculture Canada is still ongoing, and we are working with lots of countries through the JCAM project of GEO, Group on Earth Observation. Is affiliated to UN and FAO. They are publishing, and we have a few other papers, but this papers was leading by my team. So I put here, if you are interested, you can download the paper and have a very, okay, thank you very much. I think it's my last slide. Yeah.